If you're gearing up to take AP Chemistry or Gen Chem and a few years have passed since you last took a chemistry course, then this video is for you. I'm going to quickly go through bonding and nomenclature, a topic you are absolutely going to see in this next chemistry class. So let's just jump right in. We're going to start with a warm-up, see what you remember, and then I'm going to teach you everything you need to know to understand the nuances of nomenclature or the naming systems used in chemistry. So which of these four choices represents the correct formula for magnesium phosphate? Go ahead and pause the video here. Try it out. Let's see what you remember. All right. Hopefully that gave you enough time. Let's break it down. We know magnesium is Mg. If you don't remember that, it's your only option, right? Magnesium is going to come first in the chemical formula. You'll see that in all four choices. Now, phosphate. What is that? It's one of the polyatomic ions that you should have memorized. It is PO4. But what's its charge, right? That's going to matter too. So right away, we can rule out A and B. A is magnesium phosphide. B is completely made up. And then C and D technically could both be magnesium phosphate. However, we have to remember phosphate has a charge of -3. So the only correct option is going to be answer choice D. So if you actually chose answer choice D, pat yourself on the back. Maybe you don't need to watch this video. Maybe you do. Let's continue. So by the end of this video, the goal is for you to be able to discern between ionic and covalent compounds because you need to think about that before you can name them. I want you to be able to name any ionic or covalent compound, give the formula if you're given the name, and that even includes the transition metal. So let's keep going. So let's start with the basics. How would you even decide on the name if you don't know which type of compound it is? So these are the two types of compounds we're going to focus on. The first type is an ionic salt, basically. So any ionic bond is going to be classified as a salt technically. So this is where a metal is bonded to a nonmetal typically. Really what you need to focus on is the fact that electrons are transferred from the cation to the anion, which develops this ionic bond. So it develops what's known as a crystal lattice. That's what gives it this really fun shape. Versus a covalent molecule, we're going to have two or more nonmetals which are going to share the electrons. Those can be shared evenly or unevenly in a polar covalent bond, but that's a topic for another video. So an example of that would be this water molecule that I'm holding or sugar. All right, so how do you really tell the difference between the two? Look for the metal versus the nonmetal. That's the easiest indicator. There is one exception, and that one is on here, but I want you to take a second to try to identify each of these 6 compounds. Is each one ionic or covalent, and how do you know? Okay, hopefully you've had a second to do that. So right away, I'm going to pull out all of the ones that have metals. It's really easy to immediately identify magnesium sulfate and aluminum chloride, AlCl3, as ionic compounds. Now for our covalent compounds, we're looking for 2 or more nonmetals or 2 things that are on that right side of the periodic table. So carbon dioxide, C6H6, that benzene, NO2, all of those are covalent compounds. So now we're like, okay, what about ammonium phosphate? Number one, what is ammonium? Ammonium is a polyatomic ion. It's NH4 with a charge of +1. What happens in this compound? We have ammonium with a +1 charge, phosphate with a -3 charge. Guess what? We have a transfer of electrons. So even though we don't have a metal in that, ammonium is our exception. That is going to be ionic. All right, so here are the 6 compounds placed in the correct order. So that's the first thing that you really need to establish, is that you understand the difference between ionic and covalent compounds because, of course, we have different rules for how we name and write the formulas of each. Other things you might need to know, just understanding the distinctions between the properties of ionic versus covalent compounds. All of this goes back to the electrons and how those electrons are either transferred or shared, really what's going on with those bonds. So an ionic substance, when I dissolve this salt in water, it's going to conduct electricity because guess what? All of these ions separate, and that's what allows charges to flow. If I take a covalent molecule, it does not separate out into ions in solution, therefore it's not going to conduct electricity. There are some other different properties listed on this slide. Feel free to look at those or screenshot this so you have them. All right, moving on to chemical formulas. So let's start with the harder one. Ionic formulas are going to be more difficult to figure out, but they're not that hard. First thing you always need to do is determine the charge of each ion. Then you are going to crisscross the charges. So basically you're going to take the charges, ignoring the plus or minus, and create those subscripts on the opposite portions of that formula. Then you'll write the chemical formula with only the subscripts. Again, charges are not included because basically what we're doing is we're cross-multiplying to make sure that our whole compound is neutral. All right, so how do I figure out the charge of each ion? Do I just have to memorize that? No, you do have to memorize the polyatomic ions, but thankfully we can use the periodic. So if I'm working with a monatomic ion, what does that mean? Mono is a prefix that means one. I'm looking at just a single element. I'm just going to use the periodic table. So the group, again, groups are columns that the element is in. It's going to determine its charge. So sodium, for example, is in group 1. Sodium, just in case you forgot, weird symbol, Na. So that means it's going to have a charge +1. It has one valence electron. It's a lot easier for it to give up that electron, becoming a positively charged cation, than it is to gain 7 electrons. So basically, we follow that pattern. The exception is those middle groups, right? So that middle group, those are the transition metals. Unfortunately, most of those can have varying amounts of valence electrons, and therefore they have varying amounts of charges. So when we look at those groups, you see the +1 in column 1, +2 over column 2, the next large column above boron +3. Carbon can be plus or -4. That one's kind of tricky. But then once you hit nitrogen, think nitrogen negative. So that's when we switch. We have 5 valence electrons. These ions are going to gain electrons in order to fill that outer shell. So when you gain a negatively charged electron, you become negative. All right, I just talked a lot. Hopefully that makes sense. If it does not, leave a comment and I will respond to it or link you to a video. All right, so polyatomic ions, I've kind of hinted at this many times. These are the most common polyatomic ions. It does help so much if you just have these memorized. I have free flashcard sets. I'll link that right in the description of this video so you have those and you can just memorize these. And you don't want to just memorize the formula, memorize that charge. It is very important. All right, let's practice. So let's start with something simple. So if I have the name potassium oxide, potassium is a metal. I know it's a metal, therefore this is going to be ionic. So I'm going to find the charge of each. I find potassium, it's in column 1, means it has a charge of +1. Oxygen is on the far right side, 2 away from the noble gases, that last column. That means it has 6 valence electrons. It's going to gain 2, gaining a charge of, or becoming a charge of -2. All right, so now that I've found the charges of each, now I'm going to move to step 2. I'm going to take those charges and we're going to crisscross them. So that means our superscripts, those numbers up high, become our subscripts, the numbers down below. So instead of K +1, O -2, this becomes my actual formula. So that's going to slide in. Again, I get rid of the charges. I'm not going to include those because I'm essentially just cross-multiplying this. My chemical formula is going to be K2O for potassium oxide. All right, so we found the charge of each portion of the formula. We crisscross those, removing our negative and positive. If we needed to, we could simplify this down. So let's say I ended up with K4O2. You always want to simplify down to the smallest whole number ratio. In this case, we didn't have to for this one. All right, moving on. So how does that change with a polyatomic ion? So now let's look at magnesium nitrate. We looked at magnesium earlier. Magnesium has a charge of +2. Nitrate is another really common polyatomic ion. It is a NO3 with a charge of -1. When we crisscross those, how do we show that I have 2 nitrates? Can I just change that into O6? No, you want to make sure you show that there are 2 nitrates. So you're going to use parentheses. I think I was probably holding up my hands doing that. So what we're going to do is we're going to put the polyatomic ion in parentheses, and then the 2 goes outside that. So in math, you always have the number before parentheses. In chemistry, of course, we have to be different. It comes right after the parentheses. All right, so what are we going to do? You're going to identify the charge of each ion in an ionic compound. You're going to place parentheses around the polyatomic ions, and you're going to make sure to simplify it down to the simplest whole ratio. The best way to get really good at this is just to practice. There are so many options. I'm going to link a problem set so you have that. You can try that out too. All right, so now let's switch gears. We just looked at how to take a chemical name and change that into a chemical formula. Now let's look at nomenclature. Nomenclature is just our system of naming in chemistry. Why do we have to make it so difficult? I will never know, but my goal is to make it a little bit more understandable for you all. All right, so what are we going to do? When it comes to ionic compounds, you're going to keep the name of the first element, typically the metal, the same. Not going to change the ending, not going to add prefixes, do anything fancy, just write the name of the metal. Then you're going to change the ending of the second portion, the anion, to IDE, if it's a single element. So if we have what's known as a monatomic ion, so let's say I had that K2O that we had earlier, right? That's potassium oxide. So not potassium oxygen, we're going to change that ending to IDE. If a transition metal is included, we have to be a little bit more complicated because those transition metals can have varying amounts of valence electrons. So what we have to do basically is show what the charge is of that specific one. And we'll get into that in just a little bit. All right, so the best way to master this is to practice, of course. So let's go ahead and do this. So we have MgS here. What are we going to do? We're going to keep the name of the first element the same. So that is magnesium again. And then we're going to take that monatomic ion, that S, instead of magnesium sulfur, we're going to change that to magnesium sulfide. And that's it, right? That's not so bad. What do we do with these, right? All of a sudden I have all these extra elements in there. What am I going to do? Oh, you're going to have the polyatomic ions memorized. You're going to look at NH4 and be like, oh, that's ammonium. And then CO3, that is carbonate. So this one, keep the name of that polyatomic ions the same. This is ammonium carbonate. When it comes to transition metals, it's a little bit more tricky, right? Just a little bit. So basically, as I've indicated, the number of valence electrons vary. So what we have to do is we have to show the specific charge using Roman numerals. There are a couple exceptions. Zinc is always +2, cadmium is always +2, and silver is always +1. I would memorize these two, unfortunately. But for the most part, what you are going to do is you're going to use the charge of the negative anion, the second portion of the formula, to kind of like solve the mystery of what the positive charge of the cation is. So let's look at this one. I have VCl5. I find V on my periodic table. It's right in the middle of the transition metals section. That is vanadium chloride. Okay, now what? How do I figure out what goes in those parentheses? It is always okay to write what you know. You know the first name is vanadium, right? You know the metal, the name of the metal is vanadium. You know that second portion is chlorine, but we're going to change that ending to IDE. So it's vanadium, parentheses something, chloride. How do we figure that out? Again, you're going to work backwards. We know each atom of chlorine has a charge of -1. We have 5 of these. 5 times -1 gives me a negative charge of -5. We have to have a neutral compound overall. So what does that mean? That means the vanadium has to have a charge of +5. So the official name of this is going to be vanadium, parentheses, 5 chloride. So that's how we're going to figure this out. So you kind of work backwards, use the known anion, the negative portion of the formula, find the net negative charge, and then try to solve for the positive charge. This one's a little bit more tricky. So we have copper something phosphate. Phosphate, we have 2 of those, and we have 3 atoms of copper. All right, so each phosphate ion has a charge of -3. -3 times 2 gives me a net charge of -6, right? But does that mean it's copper 6 phosphate? No, because I have 3 atoms of copper that are equal to that create that +6 charge. So 6 divided by 3 means that this is copper 2 phosphate. So that's about as tricky as it gets, but thankfully the math is not too difficult for this. All right, so we started with the hardest portion because once you start doing covalent, you want to do this for everything. So let's talk about how we do covalent compounds. So just a reminder, covalent compounds are 2 or more nonmetals where those electrons are shared. So we're still going to keep the name of the first element the same, and then we're going to change the ending of the second one to IDE. So how is this different? Well, the difference is in a covalent compound, right, we don't have charges. So how are we going to show how many atoms we have of each to make sure that those electrons are shared? So the answer is prefixes. You want to go ahead and memorize these 10 prefixes. The ones that always trip students up, 2 is di, not bi, 4 is tetra, not quad. Those are the ones that are tricky because they're opposite of what you learned in math class. So know these 10 because, yeah, unfortunately you'll have to use all 10. So let's look at an example of this. So water, if you want to sound really fancy tonight at dinner, here's how you do it, right? Water has 2 atoms of hydrogen and 1 of oxygen. So what we're going to do is we're going to say this is dihydrogen monoxide. So we use the prefix di to show there are 2 atoms of hydrogen, and then mono is the 1 atom of oxygen. Makes using the name to find the formula also exceptionally easy. Carbon monoxide versus carbon dioxide. It's a difference of 1 atom of oxygen versus 2. And yes, that makes a big difference. All right, I've been yapping for a while, so let's practice. Go ahead and pause the video here and try these 4 compounds out. All right, P2O5, diphosphorus, because we have 2 atoms of phosphorus, 5 atoms of oxygen, so pentoxide. SO2, sulfur dioxide. Notice I didn't have to write monosulfur. For the first element in the compound, if you only have one atom of that, you don't have to use prefix mono. Not the case when you only have one atom of the second portion of the formula though. B2H6, diboron, hexahydride, and then SCl6, sulfur hexachloride. I guess I could have put these answers up on the screen. I need to be better about this. Give me some feedback in the chat so I know how to adjust these videos moving forward. All right, so what have we talked about? So when you are naming a chemical substance, first thing you want to think about, is it ionic or is it covalent, right? If it is ionic, you are not going to use prefixes. You're also going to double check, wait, does it have a transition metal or not? If it does, you're going to include the charge with Roman numerals. If it is covalent, you're going to be like, whew, this is easy. I'm just going to use prefixes to show exactly how many atoms I have of each. So things you need to memorize those polyatomic ions, memorize those prefixes, and those exceptions. Again, the exceptions with the transition metals, you have zinc and cadmium have a charge of +2. Silver always has a charge of +1. I hope you enjoyed this video. I have an entire review course built on my website with modules like this. Just short review videos with built-in practice and quizzes just to kind of check your understanding and make sure you're walking into this next chemistry class ready to rock it.